Everyone, I'm Maithra Raghu. I'm a research scientist at Google AI, and I'm presenting our poster, Can Neural Networks Learn Nonverbal Reasoning? This is joint work with my wonderful co-authors, Qiwan Zhang and Sami Benjo. So, over the past several years, we have seen incredible breakthroughs thanks to advances in deep learning. From areas like speech recognition, computer vision and machine translation, to complex tasks like pose estimation and dialogue. But despite these empirical successes, there remain central open questions on how these deep neural networks actually work. And one of the most central questions is around how these deep neural network models actually manage to generalize. By generalization, we refer to the ability of deep neural networks to be trained on a set of training data and then output meaningful predictions on unseen data. Now, the reason that generalization remains a mystery is that prior work has shown that neural networks are also capable of some quite counterintuitive behavior. For instance, neural networks can also be trained to memorize. We can give our neural networks training data consisting of, for instance, images, but the labels on these images being completely random, and the neural networks can also learn to fit this data. So there's been a big interest in the field to understand how neural networks perform generalization and maybe get at differences between generalization and memorization. To study these questions, we posed a question of whether neural networks could learn nonverbal reasoning. The idea being that there would be some task, and to actually generalize successfully on this task, the neural networks would have to learn some kind of logic rule, some kind of reasoning principle to be able to tackle this task. So to set about investigating this question, we first proposed such a nonverbal reasoning logic rule styled task. The task is actually very simple in nature. Each input data instance consists of 4 digits from MNIST that are randomly drawn and arranged to form a 2x2 square, as shown. The top left digit acts as a key, and its value determines where in the other 3 positional locations we should look. So for instance, if the top left digit is between 0 to 3, we're going to look at the top right position. And then looking at this top right position, we simply look at what digit is there, and that gives us the label for this entire instance. So this requires us to really perform some reasoning, to understand that we're seeing all of these different digits, to understand the notion of position, and then understand how to apply this logic rule. We designed a training set in this way by using the training digits of MNIST, and then similarly, we also designed a test set using the test set digits of MNIST. And so then we went ahead to see whether neural networks could actually learn this task. And to our surprise, the answer turned out to be yes. In fact, when testing on a couple of different architectures, we found that neural networks were in fact extremely good at performing this task. They were able to generalize very, very well. But now, to really make sure that the neural networks were learning this logic rule correctly, we decided to make the task a little bit more challenging. So this, again, is sort of the picture of what each data input instance looks like along with its label. And now the key thing to note is that both in training and test, our original data set, every single one of these different positions was allowed to take all of the values between 0 through to 9. But for now, for this harder task that was really testing the ability of these networks to learn this logic rule, we looked at introducing a distribution shift between training and test. And in particular, at training time, we let the key, the top left digit, continue to take all values between 0 to 9, but all of the other 3 positions, these other 3 digits, we actually held out some digits in each one of these positions. Now, this means that the neural network still gets to see all of the different digits at training time, but it may not see a particular digit at a particular position. Now, for the test set, we took precisely the complement of the training set. We tested on all of the instances where the digits that were held out in training were precisely the digits that were used in those positions at test time. Now, returning to this question to see whether neural networks could actually tackle this task, we found that the answer was a definitive no. The results are actually very striking. We see that the neural networks that fit the training data perfectly well, but in fact, at test data do do worse than random. And the results are extremely striking. Going back to this motivating point of understanding the differences between generalization and memorization, these results gave us quite a profound insight. They told us that, in fact, sometimes neural networks were actually generalizing through memorization. In this first setting with the IID train and test data, the neural network was learning to really map, in some sense, the test data to the training data that it had seen that looked most like it. Whereas with the distribution shift data, it was unable to do this. As a step for future work, I think it'll be very interesting to investigate methods that would actually enable generalization through learning the logic rule instead of this memorization-based generalization. Thank you very much for listening.